Okay, great. So Mike's going to talk to us in the name of the solar system collaborations. Go ahead.
Yeah, great. Thanks. I'm happy to have the opportunity to talk to you about what kind of solar system science we expect to do with the LSST alert stream. I am part of the ZTF collaboration. So I've had a bunch of experience in the last few years with transients or with comets in this kind of a setting. I'm also a active objects working group lead for their solar system science collaboration. I happen to be a co-I on the SNAPS broker proposal, but this presentation represents what our collaboration, or what my view of what the collaboration really wants to see. So what do we want to do? There are several science cases that we can address with brokers and the alert stream. So primarily is we want to discover cometary outbursts, asteroidal impacts. And I'll go into detail for a few of these on the next slides. We're also interested in finding weakly active objects. We want to just discover any other kind of unusual changes in object photometric properties, whether that's color, or perhaps we can discover that an object has a rotational light curve, or potentially has a rotational light curve amplitude that can be studied with follow-up photometry. Morphological variations in cometary come. But going into some depth on the first two, discover cometary outbursts and asteroidal impacts. The reason is that these events give us an opportunity to see material excavated from a particular location on comets and asteroids. We may not know what that location is. For example, there's on the right, you see Churyumov-Gerasimenko as imaged by the Rosetta spacecraft, and this is an outburst happening, this bright material coming off the top of it. We may not know the geological context of that, but that excavation, though, still goes into the object and brings us material that may not otherwise have been made available. The same thing with asteroidal impacts, but except in that case, asteroids are usually inert objects, so they don't have any kind of mass loss. So an impact is the only way we get to see what's on asteroids, short of sending a spacecraft there. For cometary outbursts, rapid follow-up for these things is really important, especially for comets, because of the volatiles that are produced by the impact or the outburst. The gases move at 1 kilometers per second, which, depending where it is in the solar system, could be like an arc minute a day. So catching outbursts early, or at least doing follow-up studies as soon as possible, gives a better opportunity to observe those species. And this on the right is VLT-MU's integral field unit spectroscopy of a comet that had been fragmenting, and you're able to disentangle dust, C2, CN, different species, and map them in the coma and understand exactly where they come from. Or something that I like a little bit to study a little bit more is water ice absorption features in the near infrared. Comets are made out of ice, but it's actually kind of challenging to find that ice because they sublimate, and then they sublimate on the surface. They aren't actually dragged into the coma under normal circumstances. So then we also want to discover weakly active objects. The reason is this weak activity is a sign of volatiles, and the classic problem for this is in the main asteroid belt, where we have several examples of asteroids that dynamically should have been in the asteroid belt for billions of years, yet somehow they've preserved water ice below their surfaces. And under some circumstances, that water ice can be made available and they turn into comets. So we're finding them at about a rate of 1 to 2 per year, but maybe in the LSST area, they'll go up an order of magnitude, which would be really interesting to be able to study. We want to also find weak activity because it helps us understand transition objects, what it's like how does how does a Kuiper belt object transform into a comet? When does that activity start? What kind of material is released from it? Also, and closer to the inner solar system, after a comet's gone around the sun so many times, how does it transform into a dead comet? So by identifying mass loss at the present day, we get that opportunity to do the follow-up characterization. So why are these goals challenging? First of all, the alert stream contains all solar system objects, independent of whether or not what we would call a transient event in this sense, whether or not that event occurred. And that's because solar system objects are moving, so the alert stream doesn't know the difference between something that just moved or something that just became bright. But that's also, you could also think of that as an opportunity. Move my little box around in case you can't see that. Yeah, so the other problem is that the apparent brightnesses of solar system objects vary a lot, orders of magnitude. So for example, here's Comet Swift-Gehrels, which varies from 20th to 13th magnitude in the ZTF data. But that's not the variability we're interested in. We're interested in the variations from those trends. And these two data points here at about minus 80 days is a signature of one particular event. So in the context of the alert stream, we got to find those deviations. And that's where brokers can really help out. And the other sense is it provides us with the ability, a platform which we can do immediate tests for that weak activity, for extendedness in around the object. So by identifying activity, or identifying activity is challenging goal for weakly active objects because the point source dominates the surface brightness and may bias the alert stream metadata. So we're thinking that we need some additional processing, some tests on the image data in order to separate statistical anomalies from true extendedness, or just to actually find that extendedness. So how do we get there? I think this will probably take us to the end, although I have a few other slides for additional discussion. Just minimal things that a broker needs is to be able to link alerts associated with solar system objects to the LSST SS object table, right? So solar system objects have to be treated differently because of they move so much on the sky. So we have a separate table that has to be linked into the alert stream. And again, because of this different treatment, the light curve visualization, how you retrieve a light curve for an object could be different, could also mechanically work differently. We're interested in having some priority ranks based on photometric and dynamical properties. And that's, thanks. The color of comets, for example, or user may be interested in blue comets or large Kuiper belt objects or asteroids wider than a typical PSF. So those are examples of photometric properties and dynamical properties, comets, KPOs, asteroids. Those are different dynamical populations within the solar system object table. At the next level is the outburst detection, the advanced extendedness test that I went into a little bit. Then also linking the alerts, the solar system object alerts to external archives, and I have a couple examples. JPL has a database, Lowell Observatory has a database. That way we can do rank alert or rank transients, say we want impacts that happen on carbonaceous asteroids, which is ultimately would be a very fascinating thing to study. And in what I call the expert analysis, this is where we really need the imaging data to do some additional studies of the surface brightness to see how a coma could be changing with time if there's a faint tail around the object. How much time do I have left? Is that?
Minute.
Okay, so just to show a little bit about what that light curve analysis is, here's ZTF data, 3 photometry points. LSST has 5, right? So really, we need to be able to transform these all into a common color and then detrend the resulting light curve. I think that's the best way to find outbursts. And that's what I've done. The this top plot is the same comet for that big outburst that I pointed out earlier, but there's several other outbursts in that data set, and a user may want to follow up every single one of these. And yeah, so then I have a couple examples of how we could do some morphology-based analysis, do kind of a temporal filtering in order to tell us the morphology of the outburst, because that has some useful information on whether or not you want to do a trigger on follow-up studies.
So you may
last slide.
continue
Yep.
or go to questions. It's up to you.
Yep, thanks. Then my last slide is just about actual activity discovery with a different kind of test that ignores the PSF and looks at the material around it. But all these things I would consider to be highly time sensitive and can drive observations through a follow-up manager. Thanks.
Okay, thank you. Do we have questions?
Yes, Anais is asking, will larger thumbnails be something useful for the Cometary outbursts or impacts?
Yeah, exactly. That's a good point. It definitely helps. 6 arcseconds just really doesn't seem like much. Although I think this example here is pan-stars, which the plate scale is not that much different. So this is a little bit bigger, but you can tell how, we don't know what the cutout size may actually be in this kind of an example with a really faint tail. But generally comets are going to be big, and definitely we want the more information we get, the better we can tell about how that object is varying. Yeah.
Okay, thank you. We have time for one quick question. Are there more questions?
No, there's a suggestion that this discussion of the postage stamp size is a good breakout room one.
Mm-hmm.
Right, sure. Great, thank you. Thank you, Mike.
Yep.